All right, and we're back for part 2 of this study guide again, Chapter 3 Waves. This test is Tuesday. So let's look at this law of reflection. So the first thing that I want to point out, like I did in class, is you need to make sure that you're looking at these arrows. Okay, I believe that we are going to tell you which way the light is coming from. There'll probably be like a flashlight or something showing you the light's coming this way. That way you know which one is your incident and which one is your reflection. All right, so if I have this kind of like, I guess, mirror right here, some sort of shiny reflective surface, I have my incident ray coming in, which is 29, okay? Then 30, that's my angle of incidence. So my incident ray and then my angle of incidence is right here. Okay, my normal line is in the middle, 31. The other side, I've got my angle of reflection and my reflection ray. Okay, so it comes in and it bounces off and goes that way. My incident, or the event that happens, and then the reflection is kind of like my effect, right? We know that the angle of incidence and the angle of reflection are equal. They're always equal. And like we talked about in class, let me get all this out of here. Like we talked about in class, this is 90 degrees from normal to the mirror, as is this. So if you ever had to do any math to try to solve for any of these angles, you know that the whole straight line's 180. You know that half of this is 90, the other half is 90, so you may have to do some subtraction. All right. Moving on, number 34. If the angle of incidence is 30 degrees, what is the angle of reflection and what law supports that? Okay, this is a two-part question. If the angle of incidence is 30, so is the angle of reflection because they're always equivalent. And that law is the law of reflection. The law of reflection supports that. It says that the angle of reflection is equal to the angle of incidence. All right, so let's go down and do our wacky multiple choice where we have the same questions like 3 times each. And I have no idea why. 35. Only electromagnetic waves can move through B, space or a vacuum. Okay, electromagnetic waves do not have to have a medium. 36. In a transverse wave, a measure of the distance from one trough to the next trough is the wave's wavelength. It'd be the same as if it said one crest to the next crest, or one compression to the next compression for longitudinal. Okay, oops, I'm sorry. 37. In a blank wave, the particles move parallel to the direction in which the wave travels. Parallel is my key word there, and we knew that parallel was my longitudinal wave, so that's going to be C. Only electromagnetic waves can move through D, space, a vacuum. Doesn't need to necessarily have the particles of a medium to disturb. Okay, 39. The distance from one crest to the next is the wave's wavelength, D. 40. In which type of wave do the particles in a medium move parallel to the direction of the wave movement? Again, that keyword there was parallel. We know that those would be our longitudinal waves. 41. The sun's energy can move through space because it travels as, we know electromagnetic waves do not have to have a medium and they can go through empty space. So 41 is D. 42. The wavelength of a wave is the distance from one crest to the next crest, or you could say one trough to the next trough. 43. A longitudinal wave makes particles in a medium C move back and forth parallel to the wave movement. All right, and now let's fill in this table here. We have this option bank, and each one of these falls into one of these boxes. So that means that there's going to be more than one option per box. Okay, absorption. That's going to be your tinted windows, where some of the energy is actually transferred to the medium that it's going through. That's why they say paper towels are absorbent, because if you were to put them in water, that water then transfers up into the paper towel. That's why dark colors get more hot than light colors in the sun, because they are absorbing, like the tinted windows. Okay, transmission. That's going to be your clear windows to transmit or to let something go through. So that's going to be passage of light through an object. Reflection, we labeled that law of that reflected incident and reflected ray up a little bit earlier. We have mirrors or chrome on a car, reflective surfaces, and that's the bouncing of waves off of a surface. That's why you can see your beautiful self in the mirror in the morning. Refraction, that's the changing of speed when moving into a new medium. As it changes speed, going from maybe a solid to a liquid, or from the air, which is a gas, into the water, which is a liquid, it changes its speed, which then means it changes directions. That pencil looks broken, your finger looks broken, that boy putting the pole into the pool, it looked broken. Diffraction is the spreading out around a barrier. We drew that picture with the Great Wall of China that had a hole in it. Or maybe we had Ricky the Rock. You know that the reason I could hear conversations out in the hallway at the locker is because the sound will diffract and come through the my door. Or if there were a flood in the hallway, if I opened the door, because of diffraction, the water would come in to the door when I opened that barrier. And then interference, like maybe if you watched the IU Purdue Oak and Bucket game yesterday, amazing game. We know that they can have interference, like pass interference. Maybe there's some interference going on right now during the Colts game. I had talked about how constructive and destructive, how I think about my nephew, because we like to build with blocks and we like to construct or make things bigger. That's the overlapping to make a greater amplitude. So then we can do the fun part of destroying it, of destructive, which is where they overlap, and then there's lesser amplitude, like breaking something down. Okay, so constructive is crest over a crest, whereas destructive is going to be a crest over a trough. It's almost like that highest of high and the lowest of low, and when they come together, they almost cancel each other out a little bit. It's a lesser amplitude, less energy. And that's how noise canceling headphones work. Number 1, the light wave here changes direction due to refraction. Remember, it's going from air into water, so it's changing speeds as it's changing mediums, which makes it look like it's changing direction. Why does this occur? Refraction occurs when a wave changes speed. The beam of light changes direction because light waves slow down as they go from air into water. Water is more dense. Light travels faster in air than in water. Number 3, what's the relationship between amplitude and compressions in a longitudinal wave? Here's my longitudinal wave, like a slinky. It's that parallel movement with the medium and the wave. And anytime that the amplitude's higher, the energy is higher. So if my compressions are closer together and my rarefactions are further apart, I've got a higher amplitude, more energy. If the particles in my compression are further apart, it's harder to see the compressions versus the rarefactions. That's a lower amplitude, not as much of a difference between compression and rarefaction, and that's because there's less energy going through. And number 4, a longitudinal wave would be sound. Please do not say slinky. A slinky is a kid's toy. We do use it to show longitudinal waves a lot as demonstration, but a slinky is not a longitudinal wave. It is a kid's toy. A longitudinal wave would be sound. All right, so if you have any questions, go ahead and shoot me an email. I'll be checking it tonight. Tomorrow we're going to play Kahoot and do an escape room. It's going to be a much more challenging escape room than we've ever done before. So get your puzzle solving hats on. We'll do a little group work and put our knowledge of waves to the test to see if we can solve some puzzles and escape the room. All right, have a wonderful, wonderful night. Miss you all. Cannot wait to see you. Talk to you soon.